Mechanical energy. Ever wondered how mechanical energy is divided into kinetic and potential? What role does friction play, and how can the work done by this friction force decrease mechanical energy? Watch till the end, and you'll master it forever with super cool animations.
Physify. Physics animated.
In physics, mechanical energy is the sum of kinetic energy and potential energy. So mechanical energy is not just about motion, it's also about position.
You mean an object can have mechanical energy even if it's not moving?
Yeah, like an object held at a height above the ground. Now here's the key idea. Mechanical energy can decrease when forces like air resistance or friction are present. I mean friction, by the way. These forces transform mechanical energy into other forms, which we'll explore in another video.
Like internal energy?
Alright, let's look at a few examples together. We'll start with free fall. Notice that mechanical energy is conserved. The object is initially at rest at a height h above the ground, so all of its mechanical energy is in the form of gravitational potential energy. As soon as we release it, it starts speeding up and its height decreases. So if we assume air resistance is negligible, any decrease in potential energy is matched by an equal increase in kinetic energy, but the total mechanical energy stays constant. If you're enjoying this so far, don't forget to like, subscribe, and hit the bell. Alright, but what if mechanical energy is not conserved? As we said earlier, when forces like friction or air resistance are present, mechanical energy is not conserved. So part of the mechanical energy decreases due to the work done by these forces on the object. But what does that actually mean? Let's put the object back in its initial position and compare both cases at the same time. Here, you can see that when we release these two identical objects, the one on the left falls faster, while the one on the right falls slower because of air resistance. This air resistance does work on the object on the right. The decrease in total mechanical energy is exactly equal to the work done by air resistance. Keep in mind, at this moment, the objects already have velocity. They are moving. It's as if we paused the motion to explain, so don't assume they are at rest. That's why they have kinetic energy. Got it? Alright, let's look at another example. Here we have two identical objects on an inclined surface. On the left, there is no air resistance or friction, while on the right, both air resistance and friction are present. As we release the objects simultaneously, they start to speed up as they slide down the surface. You can see how their potential energy is converted into kinetic energy. But on the right side, the object is losing some mechanical energy due to dissipative forces. Therefore, it cannot speed up as fast as the other object. Feel free to rewind this part of the video, and each time focus on one side to better understand what is happening in each case. Then compare them to clearly see the effect of dissipative forces on the motion. Alright guys, let's look at one of the most common examples, the pendulum. Here, we have two identical pendulums with strings of the same length, starting to oscillate. At the beginning, all of their mechanical energy is in the form of potential energy. The pendulum on the left moves in the conserved case, so no dissipative forces act on it. But the pendulum on the right loses some of its mechanical energy with each swing. As a result, it reaches a lower height every time until it eventually comes to a stop. Pay close attention to how the mechanical energy changes in the energy bars on both sides of the screen. But what's really going on here? Let's pause for a moment. When the pendulum reaches the highest point, it briefly stops, so its kinetic energy is 0. At that instant, it has maximum potential energy. Then it moves back down to the lowest point where its potential energy is 0. And since its speed is maximum there, its kinetic energy is also maximum. Make sure you remember this because we'll need it again when we talk about oscillations. Also, notice that the reference for potential energy is relative. This time, it's not the ground. It's the lowest point of the pendulum, where the object has the highest speed and therefore the maximum kinetic energy. Here's the thing. If we leave the pendulum on the left on its own, it will oscillate forever because its mechanical energy remains constant. Alright, here's a very important point you need to understand. Where should we choose the reference level for potential energy? We shouldn't assume that the length of the string or the height of the ball above the ground is equal to h. That would be incorrect. In fact, as you can see in the diagram, the difference in height determines how much of the potential energy is converted to kinetic energy.
Wait! At this moment, the pendulum is still at some height relative to the ground. So why say it has no potential energy?
Well, good question. That's because the pendulum never goes lower than this, and at this moment, it's at its lowest position. Keep in mind, the reference level for potential energy is relative. So, to choose the reference level, we look for the highest and lowest positions, not necessarily ground level, okay?
So what really matters is the difference between the lowest and highest position.
Exactly. Another common type of question involves a curved track. Don't let the shape of the track or the situation confuse you. When you want to analyze mechanical energy, first check whether dissipative forces are present or not. Then, focus on two key things: the object's speed at a given moment, no matter the direction, and its height relative to the reference level of gravitational potential energy. First, let's look at the conserved case. The object starts from the highest point on the track with zero initial speed. Watch how the energy bars change. You can see that the object eventually leaves the screen on the left. Since no dissipative forces act on it, it keeps moving with constant speed indefinitely. Now, let's look at the non-conserved case. Again, both identical objects are released from the highest point at the same time, with zero initial speed. You can see that the object in the non-conserved case speeds up more slowly and eventually comes to a stop due to friction and air resistance. So far, we've covered the most common examples. Now it's time to test your understanding with a few conceptual questions. Some of them may look easy at first, but be careful. Question 1. 3 identical balls are released from rest from the same height along different paths. Air resistance is negligible. Which statement is correct? A. They reach the ground with different speeds. B. They have different kinetic energies at the ground. C. Gravity does different amounts of work on each ball. D. They reach the ground with the same speed. Take a moment, pause the video, and see if you can solve it yourself. All right, remember what the first step was? First, we need to check whether there is any energy loss or not. In this case, since air resistance is negligible, we analyze the problem assuming mechanical energy is conserved. The initial potential energy of all 3 objects is the same, so their kinetic energy will also be the same when they reach the ground. That means their speeds will be the same as well. So A and B essentially say the same thing, and both are incorrect. But what about C? Since gravity moves all 3 identical objects by the same amount in the vertical direction, it does the same work on each of them. Any horizontal displacement, since it is perpendicular to the force of gravity, has nothing to do with the work done by gravity on the objects. So, C is wrong. The correct answer is D. It might feel a bit strange because it looks like an object in freefall should reach the ground faster and with a higher speed. Yes, it reaches the ground faster, of course, but not with a higher final speed. The inclined surfaces in the middle and on the left only reduce acceleration, which has nothing to do with the total mechanical energy. But the final speed comes from the initial potential energy being converted into kinetic energy. So all 3 objects hit the ground with the same speed. Why? Because the initial potential energy of the objects was equal, and all of it converts into kinetic energy when the objects hit the ground. Remember, in this case, there was no energy loss. Alright, let's move on to the next one. Question 2. An object falls through the air. Which statement is correct? A. Its mechanical energy remains constant. B. Its internal energy decreases. C. Its gravitational potential energy decreases. And D. The decrease in potential energy equals the increase in kinetic energy. Pause here if you'd like, and try to choose the correct answer. Sometimes, the problem doesn't clearly say if energy is conserved or not. You have to catch the hints. Here it says the object falls through the air, not in a vacuum. Got it? Let's go through the options. A can't be right. The object is falling through the air, so mechanical energy is not conserved. It definitely doesn't stay constant. It decreases. B is definitely wrong. In a non-conserved system, some mechanical energy can turn into other forms like internal energy, so it actually increase rather than decrease. Even if the system were conserved, internal energy would not decrease anyway. Think you know why? Drop a comment and let us know. C is completely correct. As the object moves down, its gravitational potential energy decreases. This is always true. If energy is not conserved, part of it becomes kinetic energy and part becomes internal energy. If it is conserved, all of it becomes kinetic energy. I'm sure you got the idea. And yeah, you're right. The work done by dissipative forces gets converted into internal energy. Remember, energy isn't lost or created, it only changes form. We'll get into that in another video, okay? D is only true if energy is conserved, which is not the case here since the object is falling through the air and some mechanical energy is transformed into other forms like heat. That means the decrease in potential energy is greater than the increase in kinetic energy, not equal to it. Question 3. A ball falls through the air, and its kinetic energy increases by some amount. How does its gravitational potential energy change? A. It decreases by more than that amount. B. It increases by more than that amount. C. It decreases by less than that amount. And D. It increases by less than that amount. Need more time? Pause the video and think it through. Alright guys, this question is asking about the change in gravitational potential energy during the fall. Before you get confused with the wording of the question, it's obvious that as the object falls, its gravitational potential energy decreases, so the options that say it increases are wrong. How in the world can an object come down and have its gravitational potential energy increase? So, two choices are eliminated right away. Now, we are left with two other options, one of which is wrong, so we need to be more careful. Here again, the object is falling through the air, so the system is non-conservative. That means only part of the initial potential energy the object had can become kinetic energy, not all of it. So if the kinetic energy increases by some amount, the decrease in potential energy must be greater than that amount. It's as if we said that an object falls through the air and its potential energy decreases by some amount. The increase in kinetic energy would certainly be less than that amount. That's why the correct answer is A. I'm sure you chose the correct answer, didn't you? Alright, that's it for this video. But wait, we intentionally avoided problems with calculations to focus on the concepts. Because once you truly understand the concepts, the rest is just doing the math. This video is designed to be understood on multiple levels. Now go solve a bunch of problems, then come back and watch this again. Each time you return, you'll notice something more subtle, despite its apparent simplicity. But none of this really sticks without practice.
Physify, Physics Animated.